Okay, this video is going to be some detail on PV diagrams. We've worked with them a little bit, but there's some little subtleties I want you to know. So, our definition of PV diagrams, it's a graph of pressure versus volume, like so. Now, temperature and internal energy. Remember that I can use this equation, okay, to tell me temperature in terms of pressure and volume. And if the pressure goes up, the temperature is going to go up, and if the volume goes up, the temperature is going to go up. So where in this graph are the highest temperatures? It turns out biggest pressures, biggest volumes will give you the biggest temperatures. So here are where the high temperatures and high internal energies are. And then down in this corner, it's going to be low temperature and low internal energy at the origin. In fact, the origin would be absolute zero. So the farther I get from the origin, the hotter it's getting and the higher the internal energy. So an example of that would be if I had a PV diagram with this process. It starts at state A and goes to state B. They might ask you on the AP exam, what's happening in the internal energy? So we would say that the temperature is increasing for AB. The temperature is increasing, the internal energy is increasing, in both because I'm getting farther from the origin. Now, work from a PV diagram. Remember that if it's expanding, okay, that means work is done by the gas. And that W is negative in that case. And if it's compressing, work is done on the gas. Work is positive. Now, to find the work is equal to the area below the line for a single process. Work is equal to the area inside for a closed cycle. Okay, so if I had something like this, okay, P and D, and I started out here in state A, I moved over here to state B, down to state C, and then back up to A, like so. The work would be the area enclosed, the area inside that triangle. I don't go all the way down to the x-axis if I'm doing it just for a cycle. Now the other thing is, how do I tell whether it's positive or negative? Well, I look at each branch of it. So A to B, the volume is increasing, right? So work here is negative because the volume is going up. It's going from a smaller volume to a bigger volume. B to C, the work is actually zero because there's no area underneath that BC line. Okay. Then C to A, it's compressing again because I'm going from this volume down to this volume. So here the work is positive because the volume's decreasing, it's being compressed. Now for the next cycle, the overall work is negative because the negative work is above the positive work. So work is the area inside for a closed cycle, okay? And we're going to say that the sign on top wins. Okay, this one, AB on top was negative, so this would be negative work altogether. I can note that over here. Net work is negative because negative is above positive. Now, different types of, I want to make a note of something here too, because I didn't put it in here. Actually, we'll go back up to temperature and internal energy. For a closed cycle, delta U is 0 because you return to the same temperature, okay? So looking at this diagram, if I start at A, it doesn't matter how I get there, if I end up back at A, I end up at the same temperature, so the overall delta U is 0. Each piece, AB has a delta U, BC has a delta U, CA has a delta U, but the net for the entire cycle would be 0. Now, there's some definitions we need to know. Isobaric, a barometer measured pressure. Isobaric means same pressure or constant pressure. Okay, and a constant pressure line would look like this. Isochloric means constant volume. I doubt you'll see that word, but it is possible. A graph for constant volume is going to look like this. So what's unique about that one, there's no area underneath that line. So work equals 0 because the area equals 0. And if I look at this equation, delta U is Q plus W. If the work is 0, I just get delta U equals Q. Isothermal means constant temp. And that graph is going to look like the following. Okay, the reason why it looks like that, if I think of PV equals nRT, if I rearrange it, I get P is nRT over V. P is proportional to 1 over V. That's an inverse. Inverses look like that. And the other thing, if it's constant temperature, that means that it's constant U, which means delta U equals 0. The last one we need to know about is adiabatic. Adiabatic means no heat gained or lost by the system. That means Q equals 0. If I look at my delta U is Q plus W. If that's 0, I just get delta U equals W. And a graph of those looks kind of like this one. It turns out it's a little steeper, but you can't tell that just by eyeballing it. So, you should keep this stuff in mind, maybe use these notes as we're doing PV diagrams.